Now what we're going to do is we're going to zoom in into what this convolution is and how it works with ReLU, what pooling is, and we'll also see some other information. Now let's go back in the memory lane, and here we have an image of one superimposed on a screen with a 4 by 4 pixel. So we have 16 pixels, and you have to represent one in 16 pixels. Now if you convert it in grayscale, this is the matrix you will get, and these are the values of the matrix, as 0 being black and 255 being a white. So this is an example. Now similarly, we're going to take a simpler input image. So this is an input image matrix, and this matrix is 5 by 5, and as you can see, it only has some dark and light spots. So each pixel carries these dark and white spots. Now of course, we're going to take the example for simplification. So this is the input image, and this is 5 by 5. All right, we understand that. Now the concept of the convolution filter is that we want to identify features. Now let's say that we want to identify the letters A through Z, and this specific filter is trying to pick up the letter T, T for tango. So how this works in ConNets is you take a feature, in this case the letter T, and you superimpose this image or this specific configuration of numbers in a matrix over the input image. So there you go. Your 1 1 of the input image has to be superimposed with the 1 1 of the convolution filter. So that is going to be the first step. Your 120 will be superimposed by 120, 80 will be superimposed with 0, and so on for the 3 by 3 inside the 5 by 5. So you can compute the value by using matrix multiplication, and here will be a single integer value at the end. So that is the value for 1 1 in the output matrix of this specific operation. So if I want to simulate what will be the value for 1 comma 2 in the output matrix, then you're going to have to move one cell to the right. Now you see that the 1 2 of the input image is mapped to the 1 1 of the convolution filter, and so on. So this 0 this time is multiplied by 120, this 0 is multiplied by 80, this 0 is multiplied by 80, this 0 by 0, this 0 by 80, this 180 by 0, and so on. So you get an idea that you're changing one cell at a time, and you're trying to cover the entire breadth of the input image. Now once you have actually done that, so the next 2 comma 1 can be computed using this matrix of convolution filter superimposed on the next row. So this time the 2 comma 1 of the input image is superimposed by 1 comma 1 of the convolution filter. You compute the entire row of 2, 2 comma 1, 2 comma 2, 2 comma 3. Finally, you will be going to the next row and then computing for the 3 comma 1, 3 comma 2, and 3 comma 3. Now since you cannot go any further without convolution filter going out of the input image, your output matrix stays here. Of course, there is a formula to calculate what will be the size of the output. Now another fact to understand is that when you were moving, you moved one column at a time. So first we were mapping 1 1 1 1, then you are mapping 1 2 to 1 1, and so on. So you are skipping, or you are moving one column at a time. You can also move in different fashions, and these have different variations as well. So let's take a look at the calculation here. So for grayscale, the input matrix dimension would be 5 into 5 into 1. So 5 is height, 5 is width, and 1 is the depth. For this, you would apply a filter of 3 into 3 into 1 in the example as discussed below. If this was an RGB, then the input image would be 5 into 5 into 3, 1 for each color. and the depth needs to be the same for the filter, so therefore 3 into 3 into 3. So how to calculate the output matrix dimension after this convolution operation? So it's a very simple formula which you can use. Is you can take the input height weight, concerning that all the images are proportional in their height and width. So you take the input height or width minus the convolution filter height or width, and then you simply add a 1. So in this case, let's do the math. So it's going to be 5 for input height width minus 3 for convolution filter height or width. So that becomes 2. Then you simply add a 1. That'll be the size of the output matrix. So you're going to have a matrix of 3 into 3 into 1. Now this has to be sent through a ReLU layer, and the output of that would be called as an activation map. As we know, ReLU is used for activations. So in this configuration, the number of neurons is going to be 3 into 3, so that's going to be 9 neurons, and the weights are going to be 3 into 3 into 3, that's going to be 9 plus 1, that's going to be the bias. Now this is making the assumption that there's only one combination of weight and biases used for one filter.